This podium doesn't have any light, so I may struggle a little bit. Our after-dinner speaker tonight is Andrew Smith. He's come all the way from Colorado. He's not going to get up right now to talk, but he's going to talk about advances in lab and process particle characterization. Let's see. About a week after we held our January South Texas section meeting, a giant in the world of chemical engineering passed away, Dr. John McKetta. I didn't know him, but I think there are several people in this room who did know him. He was the Dean of the UT College of Engineering and Vice Chancellor of the UT system. He served as energy advisor for Presidents Richard Nixon, Gerald Ford, Ronald Reagan, and George H.W. Bush. He published over 400 papers and wrote or edited 87 books, including the 68-volume Encyclopedia of Chemical Processing and Design. He was elected to the National Academy of Engineering, and in 2009 was selected by the American Institute of Chemical Engineers as one of the 50 chemical engineers of the Foundation Age. He was quite a guy. I never met him, but I know there are people in here who did know him quite well. Now, I'm going to bring up global warming solutions every month, and this is my pitch this month. On March 31st, the AICHE at its spring meeting, it will issue a press release through the normal routes of press releases in conjunction with the spring meeting regarding the launch of the Climate Solutions Community. Copies of that press release are back at the registration table if you'd like to read it. At the spring meeting on April 2nd, we will hold a workshop, a half-day workshop. I'll chair that workshop, and I'm going to show you an agenda for it in a moment. If any of you are going to attend the spring meeting in New Orleans, please try to attend the afternoon workshop on April the 2nd. At our Southwest Process Technology Conference in October, we're going to have a climate solutions track. The next 3 months are going to focus on climate solutions. In March, Professor Mark Holtzapfel of Texas A&M is going to be our speaker, and his topic, Global Warming and Engineering Perspective. In April, Professor Pavel Zvetkov, he's a nuclear engineering professor at Texas A&M. He's going to speak on Gen 4 nuclear. And in May, Dr. Fanju Meng with the Houston Area Research Council, or Houston Area Research Center, is going to speak on extreme weather event resiliency, which of course is of interest in this area. This is the agenda of the workshop. I apologize that we have a very long room. I'll run through it. It's half a day. As I say, if you're going to be there, please try to attend. If you're not planning on attending the conference, I'll let you in free. Just drive over for a day or so and come into the workshop. I'm going to speak for a few minutes at the start of the workshop on the evidence of climate change. Then we're going to have a panel of solutions specialists, as I call them. In chemicals, which is primarily going to focus on energy efficiency, is going to be our own Jimmy Kumana. Are you here, Jimmy? Raise your hand if you're here. I don't think he's here. Professor Mark Holtzapfel, the one who's going to give us our March presentation next month, is going to speak on fuels, primarily biofuels, and then two doctors of electrical engineering, Dr. Charles Rhodes, he's up in Ontario, Canada, and Dr. Gene Preston, he's in Austin, Texas, and has spent his career working with the ERCOT challenges. They're going to speak about electricity, primarily generation. Then we're going to have group breakouts with an introduction by Mary Ellen Turnus, who's a chemical engineer and lawyer, worked environmental law for 25 years. And then we're going to have breakouts to discuss these and this is going to be a springboard for organizing this community. I'd like to recognize our two sponsors. One, a silver sponsor. They're out of San Francisco, Business Climate Leaders, and the other, Microorganic Technologies. They're out of upstate New York. I think that we can attract sponsors who are not in this area, who want to have a presence in this area, and those are two examples. You can't read any of this because the screen's too small, but we decided these are the opportunities for sponsorship. As an executive committee, we decided that we will have a rolling 12-month period. Anytime someone wants to become a sponsor, they will have the next 12 months as a sponsor, not on a calendar basis. So I just had lunch with a company in Dallas, and they're thinking about it. So this should bring more sponsorship. I'd like to thank tonight's workshop speakers. If each of them could rise when I introduce them. Jack Chosnick of Knowledge One LLC had a workshop on an effective and efficient MOC system. Jack? Okay, thank you. And Bruno Tetamanti, I probably didn't say your name correctly. He has degrees in chemistry and economics. He's the head of marketing and sales at Biazzi. Came all the way from Switzerland, I think, I don't know. He spoke on hydrogenation reactions for chemical and pharmaceutical applications. Thank you very much to our two speakers. I pulled Bruno's photo off of his LinkedIn account. I don't know how old the picture is, but when I saw that picture, I thought, you know, that looks like a young Robert Redford. And then I looked at Jack's, and I thought, well, that looks like a little bit older Robert Redford. I want to thank our executive committee. If you weren't aware, we're having elections, and they're going to go through tomorrow. You can vote tonight on a paper ballot or online. There is something set up at that far wall for online voting. So we don't have a chair-elect, but we will after the voting concludes tomorrow. The other elections are treasurer. Eureka has extended her 2-year term into this year. She's also running again. She likes it so much. She is one of the candidates, and the other is Dave Solarski. Dave, can you stand in Eureka? Where are you at? So everybody can see you. There's Eureka way back there. I thought I saw. There's Dave. Okay, so those are our two treasurer candidates. And this is basically a retirement lunch or dinner for Sanjay Sharma. His 2-year term ended last year, and he sort of stayed on until we could conclude these elections. So I'd like to congratulate Sanjay for finally getting to retire from that job. So for the education officer and communications officer, we have one nominee. Babak Rafian, I'm going to have to learn how to say your name. Are you here, Babak? Babak? I don't guess he's not here, huh? He will be the next education officer, and Aniket will continue as communications officer. He completed a 2-year term the previous person could not complete. We covered this already, Science and Engineering Fair. Please contact Matt Kolodny or me. Networking lunches. The ones that we have on the schedule near term, February 15th at the Pipeline Grill. To my knowledge, we don't have one for March 1, but we're always looking for a speaker. If someone knows of a speaker, let us know and I'll announce it. But oh, it's going to be the same speaker at both? Yes. Ah, okay. So Peter Hannick is going to speak at both. So there will be a March 1 presentation. Okay. The young professionals have selected their 2019 leaders, and I'd like them to rise. Chair is Emily Jackson. Oh, there you are. Vice Chair is Srihari Maganti. Is he here? And Treasurer Drew Hoffmaster. Past Chair is Swara Bade. So they have a plan for this year, and Emily provided this information to me. So she wanted me to tell everyone that Houston Engineers Week is February 17 to 23. There's going to be a 5K fun run, Young Engineers of the Year banquet, Student Award luncheon, and Engineer of the Year gala. So just contact Emily or one of the other leaders. Now we have some awards. And the first is to our chair of 2018. Carlos, if you could come up. Carlos was our treasurer for 2 years prior to being elected chair-elect. Let's see, work back the numbers. You were chair-elect in 2017. And then chair last year. So we'd like to appreciate your service, Carlos. Thank you very much. And Carlos got here a little late, so we're going to have to hold him over to take a picture of this later. Hey, thanks. Thank you. James Turner is receiving an award tonight for the 2017 Distinguished Service to this section. James, could you come up? It's on the... Well, come up here and show me what you... I don't know what you're pointing at. Oh, there's something here. Ah.
Yes. Oh, it's the...
Oh, my. Congratulations. Go ahead and sit down. This is going to take me a long time to read this long introduction. Tom had written this out. I wasn't aware that this was here. James is an executive process director in Fluor's Sugarland office. He has published and presented many technical articles about process design and project execution, and holds patents for a combined hydrotreater process design. He has served as a panelist at the NPRA Q&A and Technology Forum. James has served as chair-elect, chair, and past chair of the South Texas section of AICHE. He is also a trustee on the AICHE Foundation Board and has held several positions with AICHE, including member of the Executive Board Programming Committee, and several positions with the Fuels and Petrochemicals Division, including chair of the division, director, newsletter editor, and treasurer. In 2012, he received the Fuels and Petrochemicals Service Award for distinguished service to the division and industry. He was elected to the membership grade of fellow in 2016. James is a graduate of Texas A&M University with a bachelor's degree in chemical engineering. He serves on the Texas A&M Chemical Engineering Department Industry Advisory Council and the Texas A&M TEES Industry Advisory Council, and has been inducted into the Texas A&M Chemical Engineering Academy of Distinguished Alumni. Very impressive. I didn't know all of that. Very impressive. Congratulations, James. Now, why don't you come up here, Tom, and do some talking.
Okay, it's awards time. You have until May 1st to get it in. 2018 Best Applied Paper, 2018 Best Fundamental Paper, and the new one is the Best in practice paper. We didn't have any takers last year, but I think we got a few this year. We have also the 2018 Outstanding Young Professional Award. That's for the members under 35. 2018 Distinguished Service Award, and 2018 Special Service Awards. Distinguished Service is for members over the age of 35. Now, how do I advance this damn thing?
There, that right arrow.
Well,
The right arrow. Yeah.
okay, good. And the people to contact are me, or Matt Christensen, or Ryan Stevens. You can find this in the newsletter, and I think it's also online, and we also have a application form in the newsletter, and there's also one online. I don't know if it works. Okay, it's also time for the 2019 Offshore Technology Conference. We need some volunteers, and the volunteer registration deadline is probably April 10th, 2019. The OTC is 6 to 9 of May 2018 at NRG Park, the Dome. Receive free pass, parking, and all the goodies and junk you can carry away and you can attend the entire OTC. The parking's good for the entire OTC, and you may attend technical sessions. The catch is you have to attend a mandatory orientation session and serve 4 hours in either arrangements, registration, student tours, or the First Timers Lounge orientation thing. And the person to contact is me. Let's see, we got anything else? Okay, we're back to call for volunteers for K-12.
Thank you, Tom. So this is a list of all of the efforts we have underway that need volunteers. You're not going to be able to see them. I'm going to run through them real quick. K-12 events. Matt Kolodny again. By the way, we are doing a joint pilot this year with the Gulf Coast section of the American Industrial Hygienists Association. There was the American Industrial Hygienists Association approached the AICHE at a national level and wondered if we could try to pilot our K-12. So they're going to help us, and we may help them. If you're interested in helping K-12, we can use you. Houston Food Bank, another effort. Mentoring program. Matt Kolodny is putting together a mentoring program. There are a few older folks here who can give some younger folks advice, so please volunteer. Energy Day. This was October last year, and I think it's going to be October again. We need help there. University of Houston Pre-Career Fair Workshop, another one, the Houston Science and Engineering Fair we talked about. Registration table greeters if you want to greet everyone as they come in. STS newsletter. We always need help there. Website management. If you're good at solving web problems or know how to make a website run better, we could use help there. STS networking lunch program management, east side and west side. We can use help there. We do have people working in these areas, but they can use some help. Offshore Technology Conference, Tom already mentioned that. And we have a lot of historical information we'd like to scan. Now, we have two recipients who we've let until the very end of our announcements presentation. And so I just want to run through some information on these. Well, actually, William Pittman, our Human Resources Officer, is going to run through those introductions.
Their awards. Our first recipient is Dr. Nielsen, who received his bachelor's, master's, and doctorate in chemical engineering from Iowa State University in 1974. He joined Amoco Chemicals as a research engineer at the Amoco Research Center, now the BP Research Center, in Naperville, Illinois in 1974. In 1975, he went with Phillips Petroleum in Bartlesville, Oklahoma, where he worked as a senior research engineer in heavy oil development. In 1988, he joined Ashland Petroleum in Ashland, Kentucky as a research associate and leader in the light hydrocarbons group. In 1997, he joined SRI Consulting, now IHS Markit, where he retired in 2016 as a director in the process economics program. In AIChE, he was the professional development chair in Bartlesville section from 1976 to 1977, and the secretary and membership chair in the tri-state section in 1996 and 1997. He has been the author of 6 published papers and holds 14 patents. He's authored papers in topics including catalytic cracking, hydrotreating, reforming, alkylation, CO2 emission reduction, natural gas liquids, paraffin isomerization, ethylene and propylene manufacture, anionic biosurfactants, and butadiene production. He and his wife Cynthia have 1 son, 3 daughters, and a granddaughter.
Okay, well, congratulations. So you going to take another picture of us? Why not? Why not? Why not?
Thank you very much, Tom, and the section.
Our second recipient is Rick Pritchett, who received his bachelor's in chemical engineering from Drexel Institute of Technology, now known as Drexel University, in 1969, and his master's at Newark College of Engineering, now known as the New Jersey Institute of Technology, in 1972. Rick was the first in his family to earn a college degree. He worked in various process engineering assignments from 1974 to 2017 at Gulf, Chevron Phillips Chemical Company, and retired in 2017 as the manager of Chevron Phillips Olefins and NGL Technology unit. His significant projects in his career include technology selection and engineering for a 150 metric ton per year ethylene plant, development of a polyalpha olefins technology, and engineering the technology from the pilot plant to commercialization, technology and engineering for expanding an ethylene plant by 100%, modeling and optimization of olefin facilities for the company. He is a past chair of the Ethylene Producers Committee, has chaired the EPC conference for the AIChE spring meeting, and served on various EPC committees and offices. He has 4 publications in hydrocarbon processing. We have various, testimonials or commendations of his career and his success. Several have said that Rick's biggest contribution are the countless engineers that he trained and helped push to their full potential, challenging them technically to prevent wrong and bad decisions. Michelle Mahoney, general manager at North American Operations, said that Rick's name is all over their file on ethylene technologies. Whenever big products we're working on, Rick is a major factor. Ron Korn, senior vice president at Petrochemicals, said Rick is a true mentor of probably 50 to 100 engineers. He said Rick was his one-person phone-a-friend tech support at Port Arthur in the 1990s. Stephen Prusak, general manager of corporate planning and development, says that Rick is a dear friend and a colleague to many at Chevron Phillips Chemical, and he was hoping to come here tonight, but he wasn't able to make it. Rick has 1 daughter and 2 grandsons, and so congratulations on the award and 50 years of AIChE. I butchered that.
Tonight's speaker, let's see how we're doing on time here. We're doing really well. Good. It's going to be Andrew Smith. We do have audio. How did that happen? We didn't think we had hooked up audio. Now, what I really, this is the last of the announcements. I really want everybody to take a stab at answering this question. We have pieces of paper. We're going to take an early break and come back in about 20 minutes, okay? And back at the registration table, there are small pieces of paper. I want you to take a stab at answering, and this question is back there too. We're going to have a pop quiz every month that relates to global warming, and this talks about fatalities and different types of electrical production using coal, gas, hydro, or nuclear. So let's stop for a break, and in 15 or 20 minutes I'll call everybody back in and we'll start our after-dinner presentation. So try to answer a question, put your name on it, we'll have a drawing at the end for a small prize. Thank you. plugged in before we get started.
Anytime you're ready, Chief.
We're checking out the lighting here. Does it look okay over there? Looks okay. All right. I hope most of you were able to turn in a paper with your answer to this quiz. And we'll, after Andrew Smith finishes his presentation and after the Q&A, we'll have a drawing and see who won. You'll have to, of course, have the correct answer to win. Two announcements. I didn't get into my announcements presentation. The young professionals are selling Rockets tickets, and Rockets raffle tickets. And somebody back there has got the ticket or the raffle tickets and ready to take the money? Okay. And yes, see Emily. And the other announcement is that next month is college night. So wear your college colors, I was told. I'm from, I graduated from the University of Arkansas, so I may just buy myself a Razorback hat for that meeting. I don't have one yet, but it's about time I got one. Okay, let's see. There's an applause for our speaker. Andrew Smith of Sympathetic. I may have said that wrong. How is it Sympathetic? Came here from Colorado on his dime. We appreciate that. And he's going to speak to us about advances in lab and process particle characterization. Please welcome Andrew, and I'll get your presentation up. Okay, let's see. This is it here, right? Okay, you go ahead and take it.
Thank you. First of all, thank you to Tom for the invitation to come here this evening and ruin your after-dinner digestion. Hopefully I won't make it too bad. As you can probably tell by the accent, I'm not actually from Colorado. I'm from what I call very eastern Colorado. I've worked for Sympathetic for almost 20 years, and yes, the surprise, yes, I did start as a very young boy working for Sympathetic. I moved here to the US about 6 years ago to support Sympathetic's organization here, mainly working with in-process equipment. It's very difficult with an audience like this as to where to start from, because with the greatest respect, you're highly educated people, but maybe not in my world. Now, as you can imagine, I probably spend a lot of time traveling and a lot of time in, unfortunately, having dinner alone at bars. And usually a conversation starts up of, what do you do? I'm a salesman. What do you sell? Trust me, it's not that interesting. Come on, tell me, what do you sell? Machines for measuring particles. Now, if he asks the next question, that's 3 strikes and he's out. So then I can start. So I said, well, he asked the question, you know, why does anybody want to measure particles? So basically, particles are everywhere. So I'll treat you guys like the guy at the bar. Particles are everywhere. The coffee you're having this evening, a lot of the performance of that coffee derives from its grind, how finely it's ground, how well it's ground. Orange juice. How much pulp do you like in your orange juice? Very pulpy, not very pulpy? Are you interested in where and how far agrochemical sprays drift? All of these things here are affected by the particle size. Beer. Favorite subject of mine. Who drinks nitro beer against carbon dioxide beer? You know the texture and the taste is very, very different. This is derived from the size of the bubbles in the beer. So the reasons that we look for particle size control is to control texture, control taste, control bioavailability of materials in the body. We want to check the flowability. Cement, a lot of the cement, the setting behavior is controlled by the particle size. Packing behavior in things like tablets, or if you're working with powder metals and making sintered bodies, the particle size in here is very, very indicative. If you're grinding minerals, the flotation performance, the liberation of the mineral is actually indicated by the grind. It's very important. And of course, as Tom seems to be very much on the subject, we're trying to do this using the minimum amount of energy. We're trying to get the maximum throughput, trying to minimize dusting, trying to optimize the performance of everything, minimize waste. So these are why we spend a lot of time and effort and money trying to control particle size. Now, as I think most chemical engineers and engineers anywhere will say, if you want to control something, first you have to measure. So, if you want to measure particles, there are really three things to consider. First thing, sampling. Second one is the dispersion of the material, getting the particles in the appropriate physical state to measure, which we'll come back to in a second. And the third one is using appropriate detection technology, measuring an appropriate way to get the information out of it that you want. And only by considering these three things can you really start getting a good representative measurement. As you would expect, life's never easy. Sampling. The errors related to sampling are highly related, for example, to the particle size. So, for example, if you have very fine particles, it's usually very easy to get a representative sample, and this goes off into the clouds as soon as your particles start getting bigger. You need to take more and more, get more and more error, potentially. The second one is dispersion, getting the particles physically apart. If you're working down in the nano range, this can be extraordinarily difficult to get the particles away from each other to measure them. The third one here, it's a little iffy, the analogy, but the type of instrumentation you use also is very, very important in the selection here. And usually you find, for example, depending on the technology, as the particles get bigger, they become more and more difficult to measure. Also, at the fine end, they become more difficult to measure, very dependent on the technology. So, sampling. I could go on for 3 days just on sampling, but don't worry, I won't. It's critical. I often say to people, if you don't take care at this stage, don't buy this lovely expensive instrumentation that all of us guys sell. Go to the dollar store and buy one of these calculators with a little random button on. And then just press that. Yeah? It's because that's how useful your measurement is. Okay? So it's really critical. What affects how good the sampling is, basically, is determined by the sample size, as we've seen already, by the number of subsamples, by the particle size, by the width of the distribution. I often say to people when they ask me about how much sample should I take, I say, well, let's go to one extreme. If you have a mono-size distribution, measure one particle. Yeah, that will tell you everything. At the other end, if you have a broad distribution and you're trying to understand what's happening at the coarse end, you need to be representing these coarse particles. So really, there's no distinct answer, but you really need to do the work. I spend a lot of time in laboratories as well. Quite often I see people trying to analyze maybe a 10,000 ton per day process on 5 milligrams of sample. This is not really easy, not really representative. So just think about these things. The great thing I often see as well is people take just a spatula full from the top of the jar, take a few milligrams from the top, and then the next thing is, does everybody do the same thing? Because you often find that 9 o'clock Monday morning, everybody's very enthusiastic and will do things beautifully. 3 o'clock on Friday morning, they won't do this as well. Everybody does it differently. You need to trap this. Therefore, if you're looking into sampling, you maybe could do to investing something like these, spinning rifflers. here are riffle boxes. We don't sell them. This is not a commercial. Okay? Can be totally honest about this. But these things here are beautiful. I mean, we make reference materials, and we take maybe 1 ton of silicon carbide, and we use a system like this to riffle down into 1 gram little jars. So you can imagine the number of operations that takes to do that. So this is what we use to get representative samples from 1 ton. These things are quite nice and easy. I work, for example, with frac sand guys, and the frac sand guys tend to use these sorts of things. Very simple, very fast. Please consider this if you're in the laboratory. As I mentioned, we also work in the process. So if you're working in the process, you can actually spend time and money and effort getting a good sample. There are lots of different types of sampler you can use to get a sample from your process. All sorts of different manufacturers, and if you're looking to buy sample systems, get a few people in to talk about it. Don't let somebody sell you something from a brochure. Get them in to walk your process and really understand what you're trying to do, because it's absolutely critical. This is something here which you maybe haven't seen before. This is something called a twister sampler. So what this sampler is doing, unfortunately the sound's on, I don't have to turn it down. What this is doing, this is attached to one of our systems, and it's automatically pulling sample all the time. The finger is in motion here. So it's spiraling around. You see it covers the cross-sectional area of the pipe here, so the powder is moving down the pipe. Unfortunately, you can hear the sound. What we even do is we change the speed of the motor so the tip is always traveling at the same speed, even though it's in the center, it's at the edge. And on this particular one, what it does, after every so many cycles, it will come and you'll see it cough in a second. So it actually coughs to clear itself out after every cycle, or every n number of cycles. So the point of this is we're taking a sample from every part of the process, and we're analyzing this. Now, some people say, well, why is this important? Well, this is a jet mill. Now, some work had been done on actually flow straightening the effluent from this jet mill. And what you'll see here, for example, so we have the D10, the D50, and the D90 on the particle size here. So this is particle size. Here is the concentration. So rather than what we normally do with this sampler system is we take one integrated measurement of the entire scan, here we can actually do a time slice. So this is actually distance in the pipe. So you see here, you've got massively different particle size and concentration all the way across the pipe. And this is after a flow straightening as well. And what makes life even better is that if you change just a small parameter, for example, the extract speed, all of these positions change. So this is why you must take incredible care in sampling from a process, because these things happen all of the time. And if you think that you've got your sampling set up once and your process parameters change, you're probably sampling something different. Now, dispersion. Little history. Sympatec started in about 1982. A bunch of German engineers from the University of Clausthal-Zellerfeld in Germany. They were working on improving classification systems, so air classifiers. And what they realized that they wanted to do was feed the classifier with a dispersed field of particles. Okay, so get the particles apart, because if you don't do that, the classifier sees this agglomerate as a large particle and rejects the particles. So you're getting rid of very good quality product. So they were working on industrial scale deagglomeration nozzles. Okay. The problem was that then they also needed to analyze, and they realized that what everybody was doing at the time was taking their lovely dry powder, putting it into a liquid, adding some soap into it, adding sonic energy, stirring it at different rates, and they said, well, this is nonsense. We're changing the phase here. So they then used their knowledge of industrial scale to build an analytical scale. And this is what started the entire company. I mean, originally this bunch of guys were going to sell it to the existing laser diffraction manufacturers. Every one of them said, who needs to do dry powder measurement? So being a bunch of, with respect, quite German, arrogant people, they said, to hell with you, we're going to build these. And some guys from the physics department were called in to build laser diffraction systems from first principles, and that's how Sympatec was born. We are still a privately owned company. We're still run by what I lovingly called our German technical lunatics. So we're still run by physicists and engineers and mathematicians, Even our chief accountant is a physicist. I mean, I know this because my salary seems to go into a black hole sometimes, and I don't know. So, dispersion. Always consider the state of the material in the process. Basically, the mantra is, if you've got a dry powder, measure it dry. Don't change phases. Also, when you come to measure, consider changes being caused by your sample preparation. It happens so often here. This one here, dissolving fines. It's just amazing how many times this happens. People will look in their solubility tables and they'll say, oh yeah, my material is insoluble. Yeah, apart from if you've got 5 milligrams of powder, 1 milligram in 50 mils is extraordinarily fine. This will disappear. I was actually working on a cement plant up in Idaho recently, and I was finding fine powders. They weren't finding it. It was a cement plant. And then I discovered they were analysing their cement in water. So, of course, all the solubles went immediately. So it does happen. Be careful that you don't create artifacts, either by causing agglomeration or by breaking agglomerates that are in there. Okay? Be very, very aware of this. So these two things. And the next one is release of fines. This is quite interesting. This here is something pretty typical. This is a bit of work I did just after I joined the company in the early 2000s, and I've carried this with me because it's just so instructive. I went to see a client here, and they traditionally had done their analysis wet. This is this blue one here, if you can see. I came along with my dry powder system, all young and enthusiastic in those days. Now I'm just older. And I did this. I did my work. You notice it's finer, got this fine tail. Now, first thing she said, this lady called Dr. Leslie Mackin, who's a very famous person in the field of particle characterization, she said, you're breaking my particles. It's not an unreasonable thing for her to say. But you notice, first of all, if I'm breaking particles, why am I not breaking the big ones? So we did some more work and could prove that this was absolutely stable. We also, when we added more energy, this was absolutely stable, this dry measurement. So being a real scientist, this lady said to me, okay, I'll get some micrographs done. And lo and behold, you will no chance of seeing this at the back, guys. You should have brought binoculars or opera glasses today. It was coarse particles with a fine population. Yeah, so the problem was that in a liquid system, you could not physically get these particles away. The viscosity of the liquid was just too high. You couldn't release these things. And she actually produced a paper on this in 2003 because for the first time ever, this person managed to correlate particle size and surface area and dissolution measurement. And it all comes down to getting the fines away from the coarse. It's absolutely critical in measurement. So how do we do this? Basically, we do this using compressed air and velocity gradients. So basically what we do is we get the particles to spin at a very, very high velocity. We also get particles colliding into each other, and we get collisions between the particles and the wall. And we can do this using variable amounts of energy. So how does this look? This is all made out of steel, by the way. So what we have here is our dispersing system, into which we put in a driving gas, air, nitrogen, whatever you want it to be. This creates, obviously it's an eductor, so this creates a depression. You'll see in a minute why I call it a depression, not a vacuum. So we pull the particles into here, and this is where we do the magic. So we get the particles to spin at a very high rate. We accelerate them along this little acceleration section here. This is all made out of steel. And then we just relax them a little bit. And then what we do is we fire them out the end of the dispersing nozzle. Because we're in a country using freedom units, this is about 200 miles per hour. Okay, so the particles coming out about 200 miles per hour, flying out the end here. Crucially, you'll notice, once we move the particles, we don't send them around any corners. We don't want to induce any shear or any damage. So this is how we're able to disperse without breaking generally. Needle-shaped particles are a little tricky, but this is what we do. So you see here, this is an actual measurement of it here. So these are the particles flying out the end of the dispersing nozzle. Here is our laser diffraction system. So you see, just cycle through again. I think it's going to cycle again. Yes, here we go. So there they're traveling through about 200 miles per hour into a vacuum nozzle. That's why I don't call the other thing vacuum, by the way. That's why I call it depression, because people think that it's the vacuum that's driving everything, and it's not. So there's just a gap here. You'll notice there are no cells, there are no windows. This is actually the unit in operation here. So this is quite a nice thing. So you see here, fast analysis, a few seconds. You can use variable sample amounts. People like Starbucks and these guys, which are a big market for us, the coffee market is very big for us, they're using about 200 grams generally. They're taking a nice big sample directly in. We can use less than a milligram. My personal record is 50 micrograms of inhaled drug, sort of sub 5 micron inhalation. We have very little cross-contamination because the unit is almost self-cleaning, because the particles are running through at such high speeds, they clean the actual dispersing unit as they go through. And there's this thing about variable energy input. Now, I want to introduce something here about cohesivity and what I call the theory of the apparent particle. So if you think about it, if you have sticky particles on a low-energy process, like a low-energy mixing process, the dominant particle in your process will be an agglomerate. And what are we trying to do? We're trying to produce a measurement which understands a performance. So again, we should try and set up the dispersion conditions which preserve the agglomerate. So just got a little example here. This is some micronized lactose. Here at the bottom, we have the pressure. We measure the energy in terms of the air pressure or gas pressure. So we're running here between about 0.3 bar to about 3 bar. And here we've got the D50, so the D50, the D90, and the D10 particle size. And you'll see at low energy, the particle size takes off because you've got agglomerated particles. Out here, sort of fully dispersed at 2 bar, the D50 is about 2 microns. Pretty typical for this sort of material. This client actually does some work on modifying surfaces, and you'll see here, exactly the same experiment, for 0.3 to 3 bar, you'll see the dispersion profile is almost flat. So in addition to particle size, we can also get an understanding of particle cohesivity. And then you can also then try and understand what's happening in your process. Again, if it's a low energy process, probably your particle size is out here, 5, 6 microns, something like that. Really is something important to consider. Now, we've got our sample. We've got our particles dispersed, however we choose to do this. And then we can choose how we want to measure these things. So tonight I just want to talk about 3 of the technologies. Laser diffraction, I've already talked about. Dynamic image analysis here, which can give particle size and particle shape. And something you maybe haven't heard of before, which is something called ultrasonic extinction. Ooh, something exciting and new. It's not exciting and new, we've been doing this for 20 years. But what I'm not going to talk about tonight is the nano range. Not trying to hide anything, but there's only so much you guys can take at this time of the evening. So, okay, laser diffraction. Highly, highly flexible technique. It's almost become commoditized these days, which is a shame, because it's so common. Highly flexible. Work with dry powders, suspensions, emulsions, sprays. Very, very common technique. It's very, very good, particularly for fine particles. It has a very wide dynamic range, as you saw a minute ago, from being a German company, we work to ISO standards. We only talk about what's called forward light scattering or low angle light scattering. So the range there is from 100 nanometers, and we can go up to nearly 9 millimeters. Please, nobody asked me to do 9 millimeters. It's horrible. But we do have 1 or 2 systems in the world. Generally, it's up to 3.5 millimeters. The problem is, with laser diffraction, is that only the spherical size is given. So if I have a particle which is sort of this sort of shape here, you would get the spherical equivalent. Okay, so you have fibrous materials, these things, it's a very limited use. What are we measuring? Basically, we're measuring the diffraction angles. So here we have a small particle lit with a laser, and you'll see the gap between the dark rings is quite widely spaced. So small particles scatter at wide angles, whereas large particles scatter at small angles. And this is basically what we're measuring on the systems. So this is a fairly typical system, how they're laid out. We have a laser light source with a beam expansion system, because lasers tend to give small dots. So we have a wide beam here. Then we have an optical module here. Symatec are a bit different to nearly everybody else in the market. We use different optical modules, a little bit like using different lenses on an SLR camera. So what we're trying to do is we're trying to optimize the capture of this pattern. So if you're working with coarse particles, you have very shallow angles. So basically we use like a telephoto lens, yeah, to broaden out these angles here. And we're capturing this on a detector. The detector here is mounted on a little XY motor plane. So before every measurement, there's a little Mercedes badge in the center, and we move it around until we get alignment, then we can measure. The actual detector itself has got 31 rings, semicircular rings. Usually we have semicircular because every diffraction pattern has an order of symmetry, so we're trying to capture as much of this as possible. And you wouldn't want to know the price of a full circular one. It's incredibly expensive. That's why semicircular is a good compromise here. So then, famous word here, dispersion. So here you can put your particles into this measurement zone here, and then we capture the diffraction pattern. Nice, good, easy, fast. We have a whole zoo of different dispersing systems here. For example, we've got liquid dispersers. We have a gravity disperser here for very big particles, which are very fragile, very friable. This one here is a dry powder and wet system, and here is a laser diffraction system which has a chainsaw put through the middle, which I'll show you why we do that in a second. So in terms of applications, pretty common to use these in cement. So we're trying to control the fineness of the final cement. Is there any cement people in this evening? Anybody? No? Oh, good. No experts. I like this. Very, very energy intensive grinding. So obviously what these people are trying to do quite correctly is just meet the specification that they need to meet, not overgrind, because it's huge amounts of energy. And ideally, you'd like to have a process controlled with nice particle size here. So just to show you here, this is a fairly typical result of our system. So we have 5 individual results here, and you see this is a cumulative curve here where they're really taking the numbers, and this one here is the differential of this. This really tells you where your peaks are. So you can see that as a little extra population here. Don't worry about this. This is an artifact of the mathematics. They all do it. So you see here, this is the sort of precision you should be expecting. So if you're trying to control a massive process using massive amounts of energy, you should start with precision in the measurement. And this is what we like to try and do. Sound. We also integrate these things into robotic labs. So this is an industrial system. Just turn the sound off if you would. I know. The sound's here somewhere. Oh, there you go. Magic button.
Yeah.
Wonderful. You can hear my wonderful voice even better now. So what we have here is the robot simply takes, there's a sampling system on the process. The sample gets sent to the lab using like the transport systems you have at the bank, if you're at the drive-through. Little sample splitter, and then the sampler, the robot comes along and just throws the sample in. Very, very nice. There's several manufacturers doing this because people are expensive. Surprisingly enough, we do sell a lot of these and work with a lot of these automation systems out in places like China and Thailand, which always surprises me. You think maybe labor is cheaper there, but apparently what they're looking for is good value. It always surprises me in China how much they will invest in technology. We can also do this technology directly online. This is a cement plant in Germany, not far from our home office. And what we have here is we use the customer's existing screw sampler. These things give several kilograms of powder. It's too much for us to handle. So what we have is you have a secondary mixer sampler here. So this is taking a subsample. Basically, it's a range of like fingers in the pipe. So it mixes a sample. Then we take a subsample from that. Very nice, simple device. Here we have the industrial version of our laser diffraction system. So it's the same dry powder disperser, exactly the same optical layout here. And here, these guys also wanted to do offline checks as well, periodically, so there's a little manual sampler here as well. And what these guys are doing is that these guys are trying to improve their changeover. This is quite a small plant, but they produce a lot of different grades, so changeover is critical. So what they're trying to do is hit the on-grade product faster when they change the milling conditions. and they also don't want to have an additional silo for out-of-range product. So they don't want to be blending back product that is out of spec. And this is a pretty typical output here. So we have here the 10%, 50%, 90% values here. Here they also traditionally have always looked at the percentage under 30 microns. And here, this is something called Blaine, which is a surface area calculation. This is a traditional measurement for cement people. This tends to be done manually, and it really changes according to which operator is doing it. We can calculate we call it a synthetic Blaine. And this is the measurement they're really looking at. So what they do is they start off at a high Blaine cement, drop it down, and then they decide where to change the product, and it comes back. This is actually simplified. What they normally do is when they're running steady state, they run much more slowly. They'll take a measurement maybe every 10 or 15 minutes. When they want to do a change, they'll be running every minute. So this is how they use, and highly successful application. Sprays. You know, Texas is a highly agricultural place. A lot of this work goes on. We have several systems actually in Texas doing this job. One at the USDA out at College Station, another one down at Dow in just outside Galveston. I think it's just outside Galveston doing this work. Basically what they're trying to do is they're trying to reduce spray drift. Generally it's characterized as particles under 105 microns. And they will do this by changing nozzle designs, pressure on the device, everything else, and putting different adjuvants into the spray. I'll go through this. So here is one of our customers, which is Winfield Solutions. They've installed one of our systems into a wind tunnel, which is fairly similar to the USDA one here at College Station. So they crack up the wind tunnel, get it running at whatever spray, whatever velocity they want. And this is the one that's had the chainsaw put through it. And what they do is they drive through the nozzle, through the beam. And what they're able to do is they actually have it on an XY encoder. So what they're able to do is they're able to correlate particle size with the position in the spray. It's a very nice piece of work that these guys do. So you see here they're able to run right through, measuring the particle size as they go along. It's a pretty cool little video of that. And these are the sorts of differences they can get here. So usually end up with 2 or 3 peaks. So you see one nozzle here is quite fine and bimodal. Another nozzle they're using was quite big with some big particles, which usually they're trying to avoid because they tend to overdose the material at the wrong point. So, laser diffraction. Nice, but only gives spherical particle equivalents. So let's talk about image analysis now, taking actual pictures. Again, this is quite a nice technique. Works for dry powder, works for suspensions, emulsions. It works better for slightly coarser material, up in the, I would say from tens of microns upwards, up into the millimeter. It gives size and shape, and it also gives detection of small populations, which can be quite interesting. Typical applications here, if people are wanting, for example, to look at beads, glass beads, make sure that they're absolutely the correct size, because image analysis doesn't suffer from the peak broadening that diffraction systems suffer from. We do quite a lot of work in the chewing tobacco field, because they're obviously always trying to improve their drug delivery performance and the customer acceptance. So here we have tobacco, which is often used, and they will actually measure the fiber lengths on this, and things like fruit pieces. We have a lot of systems like your Minute Maid orange juice. A lot of these are analysed on, on systems for image analysis. So basically, look at this. There are 2 main types of image analysis. One of them is static, where you put your particles onto a slide here. This is very good for fine particles because you've got your particles in nice thin layers. You can apply high magnification, and it works very well. The problem is that the particles are always oriented in the same direction, generally. They'll always fall in the lowest energy direction, which is not very good because you don't get any idea of the third. You have a problem with dispersion. That dispersion again, getting these particles away from each other. And the problem is we also have a very tiny sample size, which is not ideal. So the second way of doing this is called dynamic image analysis. Here you can use a much larger sample size. It's basically unrestricted amount of sample you can take. If you do this properly, you can get a random orientation of the particles, so you get an indication of the third dimension. And because you can dilute various ways, either using liquid or dry powder dispersion we spoke about already. You can reduce the number of overlapping particles. A lot of companies offer this sort of things, doing reflection or transmission, wet dispersion, free fall. And what we can do here is, ideally, comes back to product adapted dispersion, as you might expect from us, with good statistics. So machine here, this is called a quick pick because it takes pictures quickly, thanks to Germans. So what we're doing here, we're just feeding our sample. It comes into the feeder here. Then it drops into the dispersing system. And then you see the particles are accelerated like we discussed before. And they're coming out the end of the dispersion nozzle here about 200 miles per hour. In this particular system, this is lit by a pulsed laser with a sub-nanosecond pulse, taken up to 500 frames per second. So again, we can take a good statistic off a small amount of sample. And what we do is we're able to store the image of every particle we see on the fly, as you see in here. This is actually at 10 frames per second just for the display, but we're collecting at 500 frames per second. And we store the image of every particle off every frame in a database on the fly. It works quite nice. In terms of applications, why is shape important? Here, if you just look at the particle size, this is actually a customer who's working on graphite. They had a problem that they couldn't understand why the graphites were behaving differently. So you look at the particle size. First of all, it is by laser diffraction. Everything's identical. This is an image analysis system. The size is identical. But what happens if we plot the shape? So here, rather than a particle size distribution, we have a particle shape distribution. So all of a sudden, we plot the aspect ratio in this case, and we see all of a sudden these three materials, which are identical, are now radically different. And you see here, the high aspect ratio or low aspect ratio, whichever way you want to say it. Here, quite round particles, whereas the other batches have elongated particles. So all of a sudden, they had a new way of trapping suppliers and information and understanding product performance. The other nice thing about image analysis is detecting small amounts of material. In this particular example, you won't be able to see at the back, but this is the result of 3 million particle measurements. It took about 30 seconds. And you won't be able to see it, but there's a little lump here, a little lump in the baseline. Magnify it in. And when you do the actual measurement, because of course we can go and ask, show me the particles greater than 600 microns, for example, we see there is one particle out of 3 million. You see here. So all of a sudden, detection of very, very small amounts of material becomes very important. One application here is screen breakage. We're talking about the Czech Republic with David a minute ago. This is an application I was at just before Christmas, actually, in the Czech Republic, just outside Prague. And what these guys wanted to do was, excuse me, on their expanded polystyrene process, detect early signs of screen breakage. So what they wanted to do was here, these are two batches, one of which is in spec and one of which is out of spec. Yeah, find the difference. Yeah, obviously possible by the eye. But if you look here, the crucial thing is the particles greater than 1400 microns. And you see here, we can detect these differences reliably. This is actually an online imaging system, exactly the same as what I told you before. So this is the imaging system here with the disperser, and here it's attached to, in this case, 5, but now they've actually gone to 9 of those twister samplers. So you're getting a representative sample from 9 different process streams operating sequentially, and this runs 24/7. And the nice thing is when they get a signal saying, hey, the process is running out of specification, the first thing they do, they don't rip screens out, they go back and they can look at the data. So they can actually say, yeah, this is a real particle, check it out before we start stripping down the screens. Works very, very nicely as an application. Now, so far, we've talked about dispersion a lot. One of the big problems when you're working in a process, particularly a process involving slurries or suspensions, is dilution. You don't want to dilute. Partly because it's very difficult to take, for example, a heavy mineral slurry and dilute it and take a subsample and do it reliably. Or if you're working in things like crystallization, obviously it's a dynamic process. If you start adding liquids and everything else, you'll totally change the dynamic. So we also now use a technique of ultrasonic extinction. So how this works, basically we have a transmitter and a receiver. The slurry, or could also be an emulsion, runs between the two plates. It can also be static, it makes no difference. And what we do is very simple. We just apply an ultrasonic frequency, and we look at the attenuation at that frequency. Nice and easy, nice and simple. In reality, we make something a bit different. So this is a probe called an opus probe, and the measuring zone fits in the end of the probe here. So the two plates are usually separated by between either up to 2 to 10 millimeters in diameter, in distance, which is adapted by the machine. And what we do is we actually take 31 different frequencies. Okay, so we create an ultrasonic spectrum. Okay. So what we have here is the grey is a background fluid, which you take every 6 months if you wish. The blue here is the fluid plus the particles. So what we get is we get this ultrasonic spectrum here, and the spectrum tells us two things. The shape of the spectrum tells us about the particle size. The intensity of the spectrum tells us about the concentration. So in one measurement, we'll get both size and concentration. And you won't be surprised to see a real distribution comes out of these things. Typical example of these is on mineral grinding, copper grinding, nickel grinding, these sorts of things. We usually integrate these things into a multiplexer, partly because it lowers the unit cost, so you don't need one analyzer per stream. So we have usually 3 or 4 stage multiplexer, and what this does is just allow some of the sample through the analyzer and back out. It allows us to control the flow rate, it allows us to control the flushing. It works very, very nicely. It takes about 3 minutes per line to get this full distribution measurement. And this is the sort of information you can get out. Now, the customer originally, they just wanted this output here. They always wanted the percentage less than 75 micron. Traditionally, that's what they'd used. But because we've got this extra information, we said, use it. So the interesting thing for me here, this bottom line here is the D50 value. So, of course, this is influenced quite a lot by the fine particles in here. So you see here, even though the percentage under 200 mesh, 75 microns, is stable, the percentage here is unstable. And this is because, on this commissioning run, they were producing different amounts of fine material. So all of a sudden they had a window into what's going on with their process. But the other thing I find quite cool on this, is why I always use it, I'm an old-fashioned analyst, and I like to see this. This line here is a solid content given by the machine. You notice these downward spikes? There's some big downward spikes, so it drops from sort of 40% solids down to about 20% solids. This customer was going crazy, saying, well, is something wrong with the machine? We said, well, hang on. The solid content is derived from the same information as the particle size content. What's going on? We did some investigations and we discovered this only happened at certain times. We tracked it down to one shift. And what it was a guy on the shift who was just trying to do more than he was asked for. So what he would do, he was actually open a water flushing line. Now, this is after the cyclone, so of course the particle size is actually fixed. But he was diluting. Now, as an old-fashioned analyst, I love to see this. So all of a sudden, you've got something which is being diluted by almost 50%, but the measurement doesn't change. This shows a robust measurement. It's not affected by the concentration, as it shouldn't be at this point. It's quite a cool application. So, in summary, I can hear a sigh of relief. Summary. Sampling. Remember, if you don't think about sampling, spend $1, random number button, and do that. Yeah? That's as good as your result will be. Dispersion is really important. Think about it. Think about what else you can find out about the material. Also think about the deficiencies in what you're doing. And then use an appropriate detection technique. Is it sensitive to what you want? Is it finding these fine particles? Is it finding these coarse particles? If the shape is important, use a method which can give you some shape information. Can it detect small populations? So, thank you for allowing me to ruin your after dinner, and I appreciate your time. Thank you.
So, do we have a mic? We have a mic that we can pass around for questions. Anyone have?
Pass it around. You guys want to ask a question? Come on up.
Ah, okay.
That's good.
No? Does anybody have a question?
It was also informative.
So I have a question, Andrew. So now I'm going to tie this to climate solutions.
Yes.
You mentioned energy efficiency.
Yeah.
And one solution in the global warming era issue is reducing carbon footprints.
Yeah.
So you can help in that area in certain types of industries, you think? Improve energy efficiency and reduce carbon footprints?
Yeah. I mean, this really is an important aspect. I've forgotten the figures, but I read something the other year that something like the proportion of the electrical energy produced by the world involved in grinding minerals is something ridiculous, like 20%. It's enormous amount of energy. And, you know, if you can have a precise measurement, this means that you're not over-grinding. So I think there could be a significant impact here of several percent of the world's energy is up for grabs. Just on the energy, I was in Chile a while ago.
We're going to be talking with you.
That's good. I was in Chile a while ago, and this guy was very proud to say that they produce something like 30% of their own energy on this mine. So, fantastic. Solar? Hydro? No. Gravity? Explain. So he drove me to the top of the mine. The top of the mine was at 12,000 feet. The processing plant was at 7,000 feet. And what they did was they dumped the rock on a conveyor. And of course, they need to retard the conveyor. And they used generators on that to generate their own electricity on this. Smart people, you know, with a great solution. I love mining people. They're clever. Oh.
Anyone else?
Yeah.
I was wondering, did you do any measurements on basically smokestacks, as in just what's in our air?
We tend not to get involved in that line of business. There's some very good people out there doing emissions monitoring using different techniques. It's not really suited to what we do. We usually direct people to specialists to work in that area. We do some work with dust monitoring, you know, where people are collecting tiny amounts of powder in these little personal devices. And because we can work with small amounts of powder, we sometimes get involved in that work, but not in general environmental, no.
So you mentioned about pellets. Can you tell us how you measure pellets?
Yeah, pellets. Yeah, we tend to use that using image analysis, generally. We can get particle size, particle shape, also looking for broken pellets as well. I was working at a battery company recently, and of course part of the battery is that they make, I always forget which one it is, carbon cathode is it? And these people were working, they produce a granule, then they basically send it to a tablet press, and they just had some lack of control there. And we couldn't understand what was going on, and finally we figured out what it was when they're produced, these particles had a lovely rough surface on them. But when they vacuum transferred them across to the tablet press, under certain conditions of processing, they actually polished the particles. And we were able to see this very small shift in sphericity, as it's called, sort of surface roughness. So image analysis is excellent for that. It's an extremely good technique.
I'm not sure if I missed it. So what is the range of particles, like, you know, maximum and minimum size that your equipment can determine?
Laser diffraction runs from about 100 nanometers to up into the millimeter range. Okay. Imaging, dry, we can now go down to about 3 microns pixel size. Notice this is not politicians' words, I'm being honest with you. Pixel size, because obviously if you have 1 pixel covering the particle, you can get no information about particle shape of it. So about 3 microns, 2 to 3 microns pixel size dry, and about half a micron pixel size wet, because we're going to have a higher magnification. At the top end, it depends upon the particle shape. If you have fibers, we can go up to 100 millimeters. But condensed particles, I would say about 30 millimeters.
And how particles shape, if we have very different shapes in just one sample, how would it affect the test?
It's used all the time for particle shapes. Another interesting application I've done recently is on 3D printing, where sometimes people are using compact materials, not the granular materials, but also they also add in fiber reinforcement. And I did some work recently where the client wanted to know the size of both things. Now, because we store the information, you can then filter. So you say, okay, show me only fibrous particles and show me the distribution of only the fibrous particles. So what these people were able to do is do QC checks and research checks and actually say, okay, they're always supplying 100 micron long fibers and they're always a certain curl on there. So this works very nicely. Imaging is an extraordinarily good technique. Thank you.
Any other questions? Okay. Well, thank you, Andrew.
Thank you very much. We appreciate it.
Appreciate you coming from Colorado. We have a gift for you.
Oh, is it drinkable? You can take the boy out of Yorkshire. You can't take Yorkshire out of the boy. Yeah.
Thank you very
Thank
much.
you so much. I do appreciate it.
Thank you.
What a lovely group. Thank you very much.
Now, I'm going to ask you if you have completed your little piece of paper with your question, and it's not in this bag. Anybody have an entry that's not in the bag? No? Everybody's here? Okay. So I'm going to put up the graphic so we can talk about it. Well, I've got this now, don't I? Let's see. All right. That wasn't it. That's Andrew again. I missed it by 1. That's it. Okay. So the 4 ways of generating electric power: burn coal, burn gas. Well, these are the 4 majors, perhaps. Burn coal, burn gas, produce it by hydro, elevated water level, or nuclear. Okay, everybody know what the worst method is? Everybody think it's coal? Hydro? No. Okay, so the A is coal. Okay. What do you think the lowest level of fatalities? What nuclear? Yeah. Why do we have such an anti-nuclear sentiment in this country? Okay. We're going to try to do something about that in this community. The 2 tough ones would probably be the middle 2. So OECD, by the way, Organization for Economic Cooperation and Development, USA plus 35 other countries. So these would, be the more industrial countries, perhaps. And so the numbers are lower there than the others. Fatalities of 30,000 in non-OECD countries for either gas, or hydro? What do you think? Hydro, that's right. Okay, now we're going to have a drawing and see who got this right. Yes. All right, come over here. Oh, Emily, come on. Okay. So pull one out and we'll see if it's right. We may have to pull several out, I don't know. Okay. A, coal, B, gas. The very first one was right. I can't believe it. Ravi Saxena. Did I pronounce that correctly? Hey, come on up. Come on up. Congratulations for knowing the answer and for being lucky. All right, that concludes our evening. Next month, March 7th, we're going to be back at the Bougainvilleas on the west side, on Westheimer. And our presentation is going to be by Professor Mark Holtzapfel of Texas A&M University Chemical Engineering Department. He's going to talk about an engineering perspective on global warming. Thank you for coming. Oh, we have one more announcement. Oh, we have one more announcement. Come on.
Hey everybody, I just want to let you guys know we're planning a happy hour the week of February 22nd, and you'll be getting a news blast soon about the location, and hope you guys can make it out.
These are the YPs. Are older people invited at all, or are we? Are older people? Or can older people come?
Everybody's invited,
okay.
please.
Okay.
And also, if you want to buy a raffle ticket, please see me. And thank you for everybody who's already bought one. Yay! Appreciate it, guys.
All right. Drive safely. Okay. Good night.